Okay, so imagine, right, imagine a computer that can crunch numbers, calculations in minutes, stuff that would take the world's most powerful supercomputer, like billions of years to figure out.
Yeah, that kind of mind-blowing potential, that's what we're talking about when we talk about quantum computing. That's what we're diving into today.
We're going way beyond the hype, right, to try and understand just how close these futuristic machines are to like actually existing and working. And to help us with that, we've got some fresh research straight from the source, Google's quantum supremacy experiment.
Published in Nature. Cutting-edge stuff, really. Basically, Google's researchers, they wanted to prove definitively that their quantum computer, Sycamore, could outperform traditional computers, even with all the limitations we're working with today.
So before we get into Google and their experiment, let's make sure everyone's on the same page. What are we even talking about when we say quantum computers? What are they?
And why is building one such a challenge? Right?
Yeah, exactly. Why is that?
Well, at their core, quantum computers, they use qubits instead of bits, which is what we're all used to.
Okay.
So think of a bit like a light switch. It's either on or it's off. Represents 1 or 0. A qubit, though, that's more like a dimmer switch.
Sure.
It can be 1, it can be 0, or it can be somewhere in between, all at the same time.
Whoa.
Yeah, and this is called superposition, and what it does is it lets these quantum computers explore like tons of different possibilities all at the same time.
Okay, so, I mean, that just sounds like insanely powerful. Why aren't we all using quantum computers then? What's the holdup?
Well, the biggest thing holding us back is something called noise.
Noise.
Noise. Qubits, they're super sensitive. Any kind of environmental interference, even just a little heat, vibrations, stray electromagnetic fields, it can mess them up, introduce errors.
So it's like trying to write on a piece of paper, but you're in the middle of a hurricane.
Exactly. It's just chaos.
Yeah, it's hard to get anything done with all that going on.
And that's where Sycamore comes in. This is what Google was trying to figure out. Can they build a quantum computer that can deal with this noise and still be better than a regular computer?
So, I mean, how do you even test a quantum computer? Like, what's the quantum version of a benchmark test?
Yeah.
How do you see how good it is?
They basically came up with this, like, obstacle course for Sycamore, this really complex problem called random circuit sampling.
Random what?
Random circuit sampling, or RCS. Basically, imagine trying to predict 1,000 coins all being flipped at the same time. Like, what are the chances of getting heads or tails? It gets very complicated, very fast for a regular computer.
So they're flipping a bunch of quantum coins.
Yeah.
And they want to see if the Sycamore computer can kind of keep up with that chaos in a way that a regular computer just can't.
Right. They wanted to see if it could generate these random samples faster and more accurately than any classical computer, even the most powerful ones.
So we're not talking about replacing our laptops with this.
Yeah,
right?
no.
This is about like proving that they have an advantage when it comes to these very specific types of problems that would make a regular computer just like melt.
That's a good way to put it. It's about those tasks where a quantum computer, the fact that it can explore so many possibilities at the same time, it just gives it this fundamental edge over how we've always done things.
So they've got their quantum obstacle course, their RCS. How did Sycamore do? Did it conquer the challenge?
Well, to figure that out, Google, they went above and beyond, like a simple test. They combined experimental approaches with theoretical approaches just to make sure they were really getting to the bottom of this.
What do you mean by theoretical approaches? That sounds like, I don't know, more than just running a few calculations on this thing.
Oh, yeah, for sure. It's like they weren't just racing Sycamore against another computer. They were figuring out, like, the rules of the game for quantum computers, how to measure them fairly, even with all this noise we're talking about.
So they're creating like a level playing field, acknowledging the noise is just part of it.
Yeah.
Setting up these benchmarks. This is fascinating.
It was really important they developed all these complex models to look at how the noise affects performance, where the quantum computer starts to win, and how to measure it all in a way that, people could independently verify.
Okay, so they built this whole framework to like really put Sycamore to the test.
Yeah.
Then what? They let it loose. What happened?
They pushed it to its limits, they did.
Yeah.
67 qubits running those random circuits for 32 cycles.
So for those of us who aren't quantum physicists, what do those numbers even mean?
It's like if you had an Olympic athlete and they just shattered a world record.
Okay.
It was that level of performance. For where quantum technology is right now, it was really impressive.
Pushing boundaries.
Mm-hmm.
But still dealing with all that noise? How did they account for that in the experiment?
Well, they came up with this thing called the weak link model.
Weak link.
Weak link model
What is
to
that?
analyze how the noise affects Sycamore's performance, especially as you make it bigger. This model, what it did was it helped them pinpoint the exact point when quantum computation, it truly becomes superior to any classical methods.
So they're filtering out all that hurricane to see, okay, can Sycamore write clearly?
That's a good way to look at it.
How do you even measure that, though? How do you know it's writing clearly?
Right.
Like, what's a win in this quantum speed test?
They use this technique called, are you ready for this? Cross-entropy benchmarking.
Okay, I'm ready. Cross entropy what?
Benchmarking, or XB.
Right.
It's basically comparing what the quantum computer spits out to what you would expect from like a perfect simulated quantum computer, one with no noise at all.
Oh, interesting. Okay, so they're looking at how much Sycamore's performance like deviates from this perfect score because of the
Yes.
noise, right? Did they say how Sycamore actually scored in this benchmarking thing?
They did. Sycamore got a fidelity, hold on to your hats, 0.1% after those 32 cycles.
0.1%. That doesn't sound very good. I'm pretty sure my old laptop has a better fidelity than that.
I mean, you're not wrong. It doesn't sound like much. But you got to think about it in context, right? In quantum computing, where noise is like the biggest enemy, 0.1% after that many cycles, that's actually huge. It means Sycamore's results, they were really close to what you'd expect from a perfect, noise-free simulation, especially compared to what they've done before. But more importantly, it's way better than any classical simulation can do.
So even though it's not like perfect, Sycamore's still doing stuff that traditional computers just can't handle, even with like all the extra time in the world and no noise to mess them up. That's wild. But how do they prove that? How do you even begin to compare a quantum computer to a regular one in a way that's like actually convincing?
It's pretty complicated, but to put it simply, they used their theoretical models to figure out how long it would take the world's fastest supercomputer.
Okay.
This thing called Frontier, right? To do what Sycamore did. And get this, we're talking billions of years for Frontier to catch up.
Billions. Billions of years versus what, like minutes for Sycamore. That's not even a competition. That's just like embarrassing. This is where that term quantum supremacy comes in, right? Like this idea that quantum computers, they could just blow regular computers out of the water on certain tasks.
That's exactly it. And this Google research, it's causing such a big stir because it really does make you think, okay, maybe we are on the edge of this whole new world of computing.
But not everyone's convinced, right?
No, of course not.
I mean, this isn't the first time someone's claimed to have achieved like quantum supremacy.
Definitely not. And that's what I love about this field. Quantum computing is constantly evolving. It's this back and forth between quantum and classical approaches, always pushing each other. Remember when Google said they hit quantum supremacy back in 2019?
Right, yeah.
People came up with new classical algorithms that got a lot closer, narrowed the gap.
So it's like this like technological arms race.
Totally.
Where quantum makes a leap forward, classical catches up, and then it just keeps going back and forth.
It's so cool, this constant push for innovation.
I love it. It seems like this latest research from Google, though, it's a pretty big leap, right? Like they're really trying to address those past criticisms, focusing on why Sycamore is faster, not just that it is.
Absolutely. And they're not just tooting their own horn here. They brought in some outside experts to back them up. Like, there's this guy, Michael Fosfag,
Okay.
respected researcher in quantum computing, and he talked about how big of a deal this noise problem is and how Google is really trying to tackle it head on.
So it's not just Google saying, we're great, trust us.
Right.
They've got other people saying it too.
Independent voices, yeah.
Did they talk to any other experts?
Oh, yeah, they got Taoyang Liu.
Who that?
He's a top quantum physicist, really big name. He was talking about how important this back and forth, this competition between classical and quantum computing is for the whole field to keep moving forward.
I love that. It's not about like one side winning. It's about both sides pushing each other to be better.
Exactly.
Did anyone from Google have anything to say? Like their thoughts on the breakthrough and all that?
Oh, yeah, for sure. Sergio Boiso, he's the head honcho of quantum computing at Google. He said something really interesting.
What's that?
He said, look, this RCS thing, it's big, it's exciting, but we got to remember it's still just the beginning.
Okay, so where do we go from here? We've talked about qubits and noise and what was it? Random
circuit sampling, yeah, and benchmarking.
Benchmarking, all that. What's the takeaway for regular people? Like, what does this actually mean?
I think what it means is we've got even more proof now that quantum computers can actually do things that regular computers just can't for certain problems, and even with all that noise messing them up.
Yeah.
And this research, it's not just theoretical anymore. This has real-world
So
implications.
we're moving past, like, the can it even work
Yeah,
phase
I think so.
and into, okay, it works. What can we do with it?
Exactly. This feels different.
It feels like a turning point.
It does, doesn't it? But we still got to be realistic here. It's still early days. Sycamore, it can do this one thing really well, but it's not replacing our laptops anytime soon. The real game changer is going to be when we find those killer apps, the problems that only quantum computers can solve, where they just blow everything else away.
This is where I get a little lost. If this RCS thing, if it's just like a test, a benchmark, what does that tell us about those real-world applications? Like, what other problems out there might benefit from this quantum speed up, I guess you'd call it?
That is the million-dollar question, and that's what everyone's working on right now. But here's the thing. During this research, they said something really interesting. They said, if a quantum computer can't win at a task like RCS, it's probably not going to be good at anything else either.
So since Sycamore aced the test.
Exactly. Now it's like, okay, what else can we throw at it? The possibilities are huge.
It's like we've unlocked this door to a whole new level of computing.
And now the real fun begins.
So it's like this RCS test, passing it, it's like a proof of concept, you know? Like, okay, this crazy quantum stuff, it actually works. And now maybe those more practical uses, the stuff that'll really change things, maybe that's within reach. What could we see? What are some of those big game changers out there, the things that this could lead to?
One that comes to mind right away, material science. Think about it. What if you could design materials from scratch, atom by atom, and just like tell them what properties you want them to have?
Oh, wow.
We could have superconductors that work at room temperature, solar panels that are like crazy efficient, stuff we can't even imagine right now.
So instead of like messing around in the lab, mixing stuff together and seeing what happens, we could just tell a quantum computer, hey, we need something that does this. And it could help us design it.
That's the idea. Quantum simulations, they could give us this whole new way to look at matter, to understand it, to manipulate it at the most basic level. And that's huge. That could change everything from like how we get energy to how we treat diseases.
It's like having a microscope that can not only see atoms, but like pick them up and move them around, build stuff with them.
Exactly.
Wow. Okay, so materials, that's massive. What else? What other fields could see these quantum leaps forward?
Drug discovery, that's another big one. Right now, making new medicines, it takes forever and it costs a fortune, and there's so much trial and error involved, it's crazy. But quantum computers, they could really speed things up.
By simulating how different molecules interact with each other.
Yeah, exactly. So you can test out all these different drug candidates virtually way faster and more efficiently, and hopefully find new treatments for diseases that right now we just don't know how to cure.
That's amazing. It really is.
Aren't you there?
It's incredible to think about what we could accomplish with this technology.
And then there's cryptography, right? Which is like the backbone of, well, basically our entire digital world.
Right, right.
The way we keep things secure online, it all depends on these math problems that are super hard for regular computers to solve. But quantum computers, they might be able to crack those codes.
Oh, no, that's a little scary, isn't it?
It's a double-edged sword for sure.
Yeah, they could break the internet, but they could also help us build a new one, a better one that's actually secure.
That's the thing about this technology. It comes with so much potential, but also, some very real risks, challenges that we need to think about. And that's why research is so important, not just to build bigger and better quantum computers, but to figure out how to use them responsibly, ethically.
So this Google breakthrough, as mind-blowing as it is, we still need to, keep our feet on the ground a bit. We're not all getting quantum laptops next year, are we?
Not quite. We're getting closer, but there's still a long way to go. The next big steps, I think, they're going to be about finding those other uses for quantum computers, the things they're uniquely good at, and then actually figuring out how to build them at a larger scale and make them more reliable.
We've launched the first rocket into space. We know it's possible, but now we have to, build the whole space program, figure out how to actually get to the moon and back.
Great analogy, and we're just at the beginning of that journey, but that's what makes it so exciting, right? This sense of possibility, this feeling that we're on the verge of something truly revolutionary.
Well, there you have it. We dove deep into the world of quantum computing, looked at these amazing machines like Google's Sycamore, and I don't know about you, but I'm coming back to the surface with, a head full of questions and a sense of awe.
I think it's safe to say the quantum future is a lot closer than we think.
And getting there, as we've heard, is going to be one wild ride full of incredible challenges and mind-blowing possibilities. So keep those questions coming, stay curious, and who knows what incredible things we'll see in the years ahead. Thanks for joining us on this deep dive. Until next time.